Okay, I hope you all had a good spring break. Your next test is Friday. Before you start to panic, it's not that bad. It's over the Runge-Kutta method. It kind of looks confusing, but once you work out a few, it's not too horrible. I will say that the algebra is not hard, but it's a lot of decimals, so make sure you keep up with your decimals and you're carrying all digits to be extra precise with this one. So this is 10.1b. This is 10.1b. And yeah, we'll just get into it. Okay, so using the Runge-Kutta method, looking at this, first we need to assign our variables. So we know here that our f of t comma y equals 2t minus 3y. So it's just whatever this function over here is going to be. And we know that our y naught equals 1. We know that our h equals 0.1. And we know that our t naught equals 0, because that's what we are assuming for this process. And then we have this lovely little chart that we'll be using to solve for pretty much this whole differential equation. Okay, so to get started, I'm going to start by solving for the coefficients. I guess they're not coefficients. For these little bits, for all of our k's. So for our k1, it's told that this function is equal to k1. So our n here is 0, so we have t sub 0 comma y sub 0. So we just evaluate this function. So 2 times our t0, which we've already determined is 0, and minus our 3 times our y naught, which is 1. So we know that k1 equals negative 3. Great. So k2, we're going to do the exact same thing. We're going to come look at our chart. So we're given that k2 is equal to the function evaluated at t sub 0 plus 1/2 h, and then comma y sub 0 plus 1/2 h times our k1. Okay, so evaluating that, we get f of 0 plus 1/2 times our h there, and then comma our 1 plus 1/2, 0.1 for our h, and then we plug in this k1 value, so negative 3. And when you work that out, you're going to get a function evaluated at 0.5 for the 1/2 here, and then comma 0.085. Okay, and when you evaluate this function all the way through, you get 0.05 minus 3 times 0.085, and you should get negative 2.45. And that is your K2. Okay, K3, I'm going to go ahead and make the screen smaller so we can fit in the rest of the problem. Okay, so for K3, you can't see your little chart anymore, but hopefully you have one for yourself to look at, and I'll use one I have over here. So for K3, we have the function, and by the way, you will absolutely have this available to you. You're not expected to memorize it in any sense. You just need to know how to use it, which is what we're doing now. So don't worry about that. So we have K3 equals t sub naught plus 1/2 h, comma, and then our y sub naught plus 1/2 hk2. Okay, so evaluating this function, we get f of 0 plus 1/2 of our 0.1 for our t, and then for our y, we get 1 plus 1/2 0.1 times our k2, which we just determined to be negative 2.45. We have k3 equals our function evaluated at 0.05, and then 0.88775. And like I said, there are tons of decimals on this, and it's actually super important that you keep track of all of them, because when you're dealing with such small numbers, small deviations really matter. So try to be really conscientious about that. So evaluating this, we get 2.05, and then minus 3 times 0.8775. And you should get here a negative 2.5325. Okay, and now we only have one more. We have our K4. And our K4 is actually slightly less complicated because I like it. There's not so much plugging in. So we get our T sub 0 plus H, our Y sub 0 plus H times K3. Okay, so we have our T0 is still 0. We have our function evaluated. 0 plus 0.1 for our H, comma, our Y naught is 1 plus 0.01 times our K3, which is this number. So our negative 2.5325. Okay, and you should get these numbers. So our 0.1, comma, and then for your Y value, 0.74675. Okay, so you get 2 times 0.1 minus 3 times 0.74675, and you should get negative 2.04025. Okay, and now we have all our coefficients, and we can start actually solving for the value that we are interested in. So go ahead and make this smaller one more time, and we're just going to plug it into that general formula at the top of the chart, and we'll have our answer. Okay, so now we have all our coefficients, and so we can say that our y of 0.1 is approximately, I do say for this test probably that the tilde here is important because you are definitely approximating. You're by no means saying that these things are completely equal, because they're not. So please keep that in mind when doing this problem. So this is from your little formula sheet up here. I know you can't see it, but I'm using this part right now. So we have, actually I'll write out the whole thing, y sub naught plus h over 6 times k1 plus 2k2 plus 2k3 plus k4. And now we're just going to plug in all the values we just solved for. Tilde, and so our y naught still 1. Our h is still 0.01 over 6. Our k1, we got negative 2.45, and then plus 2 times our k2, which was negative 2.5325, and then plus 2 times our k3, which was, oh, I'm sorry, this 2, I'm trying to think how I want to do this. Our K1 is -3. So -3 goes there. And then our K2, I got a little ahead of myself, -2.45. And then our K3 is -2.53. I know my 3s and my 5s look very, very similar, and I'm so sorry, but I hope the audio helps you discern which one I'm talking about. And then for our K4, we got a -2.04025. Okay, and when you plug in all those numbers to your calculator, you should get y evaluated at 0.1 is approximately equal to 0.7499125. And that is your answer for part A. So for part B, you are given a function. You're saying that we're given that this is an analytical solution to the ODE that we've been working with. -3t plus 2/3 t minus 2/9. Okay, and all you're going to do with this part is you're going to plug in our 0.1, which was given in the first part. So we have y equals 11/9 e to the 0.1 times -3 plus 2/3 0.1 minus 2/9, and you should get there 0.74988936. Okay, and then to solve for the error in that, you're just going to take the absolute value. So for our error, we're going to subtract these two values, so we get 0.0749883, I forgot a 936, and then minus what we got over here, so 0.7499125. And like I said, absolute value on those, and you can solve for your error is equal to 2.3564 times 10 to the -5. And that is how you solve this problem. And hopefully it made sense. Please let me know if you have any questions whatsoever. If not, I'll move on to the next problem. And also, I please want to reiterate, the decimals on this are super tricky. I did this problem 3 times before I got this exact answer because I kept getting things that were very, very close, but not exact because my decimals were slightly off. And like I said, when you're dealing with super small numbers, the small deviancies really matter. So please be super attentive to how you're writing things down and how you're inputting them into your calculator. So good luck, and let me know if you have any questions whatsoever.